So folks, I wanted to do a quick video overview to this solution. The purpose of the video overview is just to mention all the steps that are made. I wouldn't encourage you to try to copy down the solution as I'm working through this video. Rather get a general idea for it, try it on your own, and then check your answer against my answer. So we're asked to use Laplace transforms to solve this IVP, where here's the ODE, and here are the three initial conditions. So let's look at the solution that I did for this. The first thing I did was I went ahead and took the Laplace transform of y triple prime, and that would be following the formula that we've given or that we derived in class. That would be s cubed y sub s minus s squared y sub 0 minus s y prime of 0 minus y double prime of 0. You can see because y prime of 0 is 0 and y double prime of 0 is 0 that these two terms will just die off here. So I'm just left with these two terms, and we know that y sub 0 is 1, and so that's how this simplifies. We do the same thing, very similar with y prime. It's a little bit easier, and we get sy sub s minus y sub 0, and that's how that simplifies. Finally, we take the Laplace transform of the right-hand side, meaning this e to the t here, and the Laplace transform of e to the t is 1 over s minus 1. So at this point, we're ready to go ahead and take the Laplace transform of both sides of this equation. So we'll take the Laplace transform of the left-hand side and the Laplace transform of the right-hand side, mapping us over into S space, giving us this new IVP where there's my y double prime, there's my y prime, and there's the e to the t prior to the transform, and then they move over. So folks, at this point, this becomes an algebra problem. And we need to solve this algebra problem for capital Y sub s. So what I did here is I collected together these two y sub s terms and then factored out y sub s. So that's how we end up with s cubed plus s times y sub s. Then we have these two non-y sub s terms which start out here, and then I add them over to the other side here. So although you don't have to do it this way, I think that it's easiest to minimize the amount of partial fraction decomposition you do. I go ahead and combine this as a single expression by getting a common denominator. My common denominator will be s minus 1. So I multiply this by s minus 1 over s minus 1, and I multiply this term by s minus 1 over s minus 1, giving me this large expression here, but that combines together to give me just a single fraction right here. At this point, I then take these terms. Notice I factored out an s, and I divide those over to the other side. And in one sense, I've accomplished my goal. I have solved this algebraic equation for the function y sub s. I have solved it for y sub s in S space. And all I really need to do is I need to just take this answer and bring it back into the t domain by taking the inverse transform. Easier said than done, though, if we don't have computer programs to help us. We're going to have to break this up into smaller components, each of which we might be able to do the inverse transform to. So what I need to do is I need to do the partial fraction decomposition on this large fraction here. So I break it up as a over s, b over s minus 1, and then careful, this is an irreducible quadratic, so remember we do it as cs plus d for that irreducible quadratic. And also because we have that irreducible quadratic, we can't use the trick that we talked about in class. Although there's some ways you can modify the trick, I'm not interested in going through those because I don't think they make it that much easier. So folks, we do have our work cut out for us, but remember, this is just the partial fraction decomposition step. So as you're looking at this problem, I encourage you to sort of separate this sort of messy, convoluted task of partial fraction decomposition from the overall sort of more elegant way that we're tackling solving the original IVP through Laplace transforms. So remember, the first thing we do for partial fraction decomposition is we multiply both sides of this by that least common denominator. So that gives me this term on the left-hand side. And then notice that the a sub s, it was missing the last two factors of the common denominator. So that's what remains when we multiply that to a. And for the second term, we're missing the factor of s and s squared plus 1. So that's what I multiply to b. And likewise, for the last term, we multiply the missing two factors. Folks, now I've just got a kind of a messy bookkeeping problem. I'm going to expand this whole thing out, expand each one of these out. And you can see that I've done that in these lines here. I then collect all of the terms. This is the important part of partial fraction decomposition. I collect all of the terms by their powers of s on the right hand side. So this has an as cubed, bs cubed, cs cubed. So I get that a plus b plus cs cubed must be equal to this 1s cubed over here. I do the same thing for my s squareds. I've got a minus as squared and d minus cs squared, and that gives me all of this. And likewise for the linear term and for the constant term. And so notice then we make the classic positioning argument where we say, hey, the coefficient in front of s cubed over here must be the same as the coefficient that understood 1s cubed here. So that's how I got my first equation. Likewise, I equate this -1 with the coefficients of s squared over here. That's how I get the second equation. The third equation, then watch the fourth equation. Notice there's no constant term, so that's an understood plus 0, which is how we got that fourth equation of minus a equals 0. Okay, so I now just need to solve this system of 4 equations, 4 unknowns, and although it's easy to identify a because I still have 3 equations, 3 unknowns after that, I don't recommend trying to solve this with standard algebra techniques. Rather, let's do the RREF, solving a system of equations technique that we've learned in this class. And so we see sort of a practical reason for doing so. So all I did was I took this, there's the 1, 1, 1, and then that's plus 0d. That became the first row here, and all of the subsequent rows became, all the subsequent equations became rows. And then I just simply did RREF form, and this took me a little while. You probably could do a couple of the steps faster if you wanted to, but I make enough mistakes with it that I chose to do it in several steps, and we get that the coefficients for A, B, C, and D are as I've listed there. Remember, these were how we were breaking this up, so A is going to be 0, B is going to be a half, C and a half, and D minus a half. So I go ahead and state that here, and this is what we end up with. Okay. After just a little bit of manipulating, notice that this term dies out. I'll be able to take the inverse transform of this term, no sweat. This term I'm not ready to take the inverse transform of, so what I do is I break it up into this right here. And waiting for that to go away. And then this right here. And so I can see I'm expecting this to give me some sort of cosine because of the s in the numerator, and this to give me some sort of sine. And in this case, we don't have too much manipulation we need to do the inverse transform. And that's not always going to be the case. And you guys have seen plenty of examples where we have to do the inverse transform, and it takes a little while to clean that up. Okay, so now that I've got this, now that I've got this expression right here, that y sub s is just equal to all of this, I just simply take the inverse transform of both sides. Folks, you don't need to rewrite this step out for me. I'm just doing that for the completion of these notes. If you want to just go from here and then go ahead and conclude what the solution to the IVP is, you're free to do so. Notice that this gives me the inverse transform of this was e to the t. And here is my sine, and notice that the in this case, a squared is equal to 1, so the a is equal to 1, so that's a little bit confusing there, potentially. And likewise here is the a squared, which is equal to 1, and here is the a, which is equal to 1. So just sort of watch that in different problems that won't necessarily be exactly like this. And we've got our solution. I hope this helps. As a reminder, folks, I don't encourage you to try to get the solution from this video. I did it much too quickly. Instead, I would encourage you to, after watching this video, try it again, see if you can do the problem by hand, and then check your solution against my key. Let me know if you have any questions, folks.